Okay, this is the solution to Hagen problem 4.17 that takes the ideas of static equilibrium and applies them to pulleys. Okay, so in this case we're assuming the pulleys have weight that it's negligible compared to the suspended mass, and we're also assuming that there's no friction that makes the pulleys harder to turn that would influence the answer of the problem. Okay, so I'm going to also add another question. I'd like to know the tension in this cable that holds up everything. Okay, so we look at this and we need some way of attacking this problem. And we know a couple of things. We know about free body diagrams. We know about static equilibrium, where the sum of forces in the x direction is equal to 0 and the sum of forces in the y direction is equal to 0. And we know about weight and mass. Okay, so we know those things. How are we going to attack this problem? All right, so I think one of the first things you do is you try to figure out, how am I going to do a free body diagram? So let's label this pulley as point A, this pulley as point B, and then we have point C, which will be the mass. Although, you know, I could argue that you'd be fine with just two free body diagrams because the one for C is so obvious. Okay, let me move this. This is the calculations. All right, so moving that down. All right, so we look at this and we say, okay, point A, all right, that looks like a cylinder, a circle, because it's representing a pulley. And we have something pulling up. Okay, that's the tension in this cable. We'll call it TA. All right. And the next thing we have is pulleys that are connected to, or a cable that's connected to different points with the two pulleys and with the person that's holding the end of the cable. Okay, so I know that the person holding is exerting a tension T based on the person's weight. Okay, we'll talk about that in a second. But then we also have a force pulling down this way, and because it's a cable, the tension has to be the same throughout the cable. All right, so I think that's somewhat obvious. Think about that. The tension can't change in a cable through a pulley. All right, it's going to be the same on either side of the pulley. All right, and then, you know, ultimately, the second cable here is also exerting a force that's given by the tension in the pulley. So we have three forces on the pulley at part A pulling down, one force coming back up. So this is the free body diagram of point A. All right, so what do you think? All right, think about that, make sure it makes sense. Okay. So maybe pause the video and do the free body diagram at point B. All right, so give that a try. All right, and so at point B, I see I have two forces pulling up. That would be the same tension T as that I had in the free body diagram of part A, because it's the same cable. Okay, and then I have pulling down a force that I would call TC. All right, the force from the suspended cylinder. Okay. All right, now let's do free body diagram for part C. All right, so now we have this cylinder, and we know that we have TC pulling up. Okay, and then pulling down, we have the weight of the cylinder. Okay, so that would just be W. Okay, so at every point I have to have static equilibrium. All right, so I'm looking at trying to figure out the tension that's required in the cable, and the tension comes from the weight of the person. All right, so the minimum weight of the person, you know, if the person doesn't exert enough tension, you know, you can only exert as much tension as you weigh. All right. If the tension required is greater than what you weigh, you'll just go zipping up in the air. Okay, hopefully that's obvious. All right, so what we see here is that TC is equal to W. All right, that's pretty obvious. Those two, sum of forces in the y direction, give me that equation. Okay, and then we know that W is the mass, which is 25 slugs, and then we multiply by gravity, which is 32.2 feet per second squared, and this gives me the answer of 805 pound force. Okay, so that's W. All right, then moving over here, I see that since TC is equal to W, that's equal to 805 pound force. And I have an equation that 2T is equal to 805. And I'm liking this because that lets me solve for T. All right, so we get T to be 402.5 pound force. All right, so that's probably going to send almost everybody up in the air. All right, so we'd take a very large person. All right, so there's the answer to the original question. And then I asked, what is the tension in cable A that suspends the whole thing? All right, and so you see, that's the power of a pulley. It lets you change the direction of forces. All right, so I can hold up a larger weight. The weight of the cylinder is 805 pound force. It only takes a person of half that weight to hold this thing up in the air. How does that work? Well, you're trading off the direction of forces, basically. Okay, so what we see here is that the tension in this cable is going to be, TA is pulling up, and then I have 3T pulling down. All right, so I plug in for that tension, and I get 1,207.5 pound force in the cable, because basically the cable has the tension of both the force due to the weight and the force due to the person that's holding the other end of the cable. Okay, so hopefully you see that, and it's brought in, this idea of using a pulley. All right, we'll talk about pulleys a little more, hopefully with another example problem. All right, but you get the idea of combining static equilibrium with a pulley.